Okay. So preparation of alkane, carbon-carbon double bonded compound is called an alkene. Carbon-carbon triple bonded compound we call as an alkene, alkyne. Preparation of alkene from unsaturated hydrocarbon. First method of preparation of alkene. Alkene or alkynes are treated with dihydrogen in presence of platinum, palladium or nickel catalyst, which gives alkane. This process is also known as hydrogenation. This process is also known as hydrogenation. For alkene and alkyne, in alkene 1 mole of dihydrogen is required, in alkyne 2 moles of dihydrogen is required to prepare the respective alkenes. Okay, and platinum, palladium, nickel catalyst what we are using, this adsorbs hydrogen, adsorbs surface phenomena, adsorbs hydrogen H2 on the surface and activate hydrogen bonds. So adsorption phenomena using of platinum is adsorption phenomena. So on the surface of platinum or palladium or nickel, hydrogen will be adsorbed and activates an hydrogen bond. So platinum palladium catalyst, the reaction at room temperature, but relatively higher temperature is required, higher temperature and pressure for nickel catalyst. For this platinum and palladium, in room temperature itself, the reaction will take place. Okay, when alkene or alkynes are heated, alkenes or alkynes are heated in presence of nickel catalyst, at higher temperature and pressure. Higher temperature, roughly 300 degrees Celsius. Okay, so in 300 degrees Celsius, this process is known as, so in the preparation, so alkyne or alkene are heated with nickel in presence of dihydrogen H2, I'll write H2 in presence of nickel catalyst, will be getting alkane, especially with the using of nickel catalyst, This is called Sebastier, Sabater, Sebastier, Senders, Senderens, Senderens, Sebastier Senderens reaction. Sebastier Senderens reaction is nothing but preparation of alkene from unsaturated hydrocarbon is nothing but alkene and alkyne using of dihydrogen in presence of nickel catalyst. This is called Sebastier Senderens reaction. So remember, so the same as an olefins. So olefins is nothing but carbon-carbon double bonded compound are treated with dihydrogen in presence of nickel catalyst, will be getting alkene. Fine. So along with that, cycloalkanes. We have in a cycloalkanes is the minimum carbon is 3. That is in CH2, CH2 and CH2. This will be treated with dihydrogen plus H2 in presence of nickel catalyst, and the 80 degrees Celsius will be getting to CH3, CH2, CH3. Closed chain into the straight chain CH3, CH2 and CH3. So this is propane, cyclopropane into propane. Alkene also prepared from cycloalkane by hydrogenation. Similarly, cyclobutane treated with dihydrogen, okay, in presence of nickel catalyst. Only in the case of the higher cycloalkanes, temperature will be increasing. In the case of cyclobutane, treat with dihydrogen in presence of nickel catalyst, temperature greater than this is 200 degrees Celsius, will be getting N-butane, normal butane. Okay, this is the method of preparations of alkene from the first one, unsaturated hydrocarbon, and the second one is the cycloalkane. From the cycloalkane also we can able to prepare alkenes. Okay. Next one is from alkyl halides. First reaction is hydrogenation, right? Second one is reduction. Of alkyl halides. Reduction of alkyl halides is nothing but preparation of alkane from alkyl halides or haloalkenes. Halo an alkene, R is alkyl group, X is an halogen group, or X is called haloalkenes. Haloalkenes. Okay, Rx is a general formula. R is an alkyl group, carbon and hydrogen group. X is group 17 element, that is an halogen. Okay, haloalkenes. This what happens, except the alkyl fluoride, it's more reactive. And apart from that, alkyl halides are treated with zinc, reduction with zinc in dilute hydrochloric acid. Zinc in dilute hydrochloric acid, which gives alkane. Rx alkyl halide. So reductant, use a reductant like Zn, zinc in hydrochloric acid, dilute HCl. So what happened? So when we used the reductant, what we use, zinc in hydrochloric acid. So this will be formed RH plus HX. RH plus HX. How it will be? Example, CH3Cl, methyl chloride, chloromethane. Chloromethane on hydrogenation, H2. So on hydrogenation means an H2 in presence of zinc or hydrochloric acid will be getting hydrogen H and Cl, HCl, H and CH3. It becomes CH3H plus HCl. CH3H is equal to CH4. CH4 is methane. CH4 is methane with the formation of hydrochloric acid. Okay, so reduction of alkyl halide, or from alkyl halide we can able to prepare alkenes. Haloalkane, halogen, X is an halogen, R is an alkane group, is called haloalkane. Haloalkane are treated with dihydrogen in presence of reducing agent or reductant like zinc or hydrochloric acid. So we'll be forming RH and HX. So we can get respective alkenes. So chloromethane are treated with dihydrogen in presence of zinc and hydrochloric acid. So reduces now CH3Cl, changes into chloride and H and chloride to form HCl, and CH3 and H forms and methane. Similarly, C6H5Cl, so chloroethane treated with dihydrogen will be getting ethane. So propane. Propane means, if you want to specifically write fluoropropane, one fluoropropane gives an propane in presence of zinc and hydrochloric acid. So this is the next method of preparation. Second method of preparation of alkene from haloalkenes. What we use this reaction? The reaction what we are using, the reductant. Okay, reducing agents or reductants, what we are using, these are zinc or copper couple. Zinc or copper couples. Okay, what we can use? We can use zinc copper couple in ethanol, ETOH. Okay, ethanoic acid, or sorry, ethanol, or sodium Na in ethanol, ETOH. Platinum or palladium, Pd, or nickel or dihydrogen H2, or aluminium or mercury, these in ethanol, ETOH, and lithium aluminium hydride, LiAlH4. These are the reductant. With the using of all these, we can able to reduce, we can able to get alkene from the alkyl halides or haloalkenes. Second year, first chapter of organic chemistry is haloalkenes and haloarenes. This is the same reaction. Rx plus H2 gives rise to RH plus HX. Okay. And here, so what the alkyl halides, this also can be prepared using red phosphorus. Okay, using red phosphorus. Example, Rx, ethyl iodide, C2H5I, treat with hydroiodic acid, HI, in presence of red phosphorus. This also acts as reducing agent, okay, and which will give C2H6, okay, I2 plus C2H5 and H, it becomes C2H6, okay, we'll be getting the alkene. We can able to prepare the ethyl iodide from iodoethane to ethene. So this is we call as reduction. Second method of preparation of alkene is reduction. In this reduction, alkyl halide are reduced with zinc in presence of hydrochloric acid using dihydrogen. Will be getting alkane RH plus hydrogen alide HX. Okay. Second one. So second method of preparations of alkene. Okay. From not only this, the two important method, we have another important methods. In the another process, another method is important process, very famous naming reaction, Wood's reaction, WURTZ, is called Wood's reaction. What is Wood's reaction? Alkyl halides alkyl halides are treated with sodium metal in presence of dry ether. Alkyl RX treated with RX alkyl halide are treated with sodium metal in presence of dry ether. Will be getting the higher alkane R 2R, 2Na. In presence of diether, we'll be getting RR plus the remaining is, okay, NaX sodium halide, respective NaX sodium halide will be getting. So, what is Wood's reaction? Alkyl halide and treatment with sodium metal in dry ether. Okay, so what is the necessity of using dry ether? Instead of water, we can use, no, why they are using dry ether? Sodium is highly reactive and it can react with the moisture. That's the reason we'll be using dry ether, free from the moisture. Dry ether, free from moisture. This reaction, this is what we are getting, the higher alkene. This is known as Wood's reaction, method of preparation of higher alkane from haloalkane. From haloalkane is called Wood's reaction. Okay, what we are using this should be the consisting of even number of carbon atoms is called as symmetrical alkane, because the cleavage has to take place. No, equally cleavage has to take place. Symmetrical alkane, carbon gets separate. 1, 2, 3. So unsymmetrical alkane. 1, 2, 3, 4. Symmetrically, we can able to separate this alkene. This is okay. This is okay. And 3 carbon and 5 carbon unsymmetrical. This is not suitable for unsymmetrical alkene. This reaction is suitable for symmetrical alkenes. Are you getting? Symmetrical alkane is one which equally can cleave, separates. Okay. So we can see an example. Rx is nothing but RBr, RR, Na, sorry, RCl, R, etc. So alkyl bromide and treating with sodium metal, Na. So Na, alkyl bromide. So I'll write in reverse 2 molecules of Rx. Can you see this? 2 molecules of Rx. I'll write 1 molecule of Rx, RBr, another molecule I'll write in reverse. So XR is nothing but BRR. Then RBR, BRR, both are same. Right? Here one molecule and here one molecule. Look here, if it's separate, no, this Na, 2 sodium combines with halide group. So this will be Na, Br and Br, 2 Na, Br. We are getting 2 Na, Br. Then R binds with an R. We'll be getting R plus NaBr. That is 2 NaBr. 2 NaBr. So Haloalkanes are treated with sodium metal in presence of dry ether, which gives higher alkene. This is called Woods reaction. What is Woods reaction? You have to remember Woods reaction. Preparation of higher alkene from haloalkene is called Woods reaction. So this can be written as RBr, 2RBr, alkyl bromide, CH3Br, or C2H5Br. CH3Br, methyl bromide or bromomethane. So this bromomethane treat with sodium Na. Na and this molecule, I'll write BrCH3, methyl bromide. This will be separate now. So it becomes CH3, CH3, Ac2H6, higher alkane. We have taken methyl bromide, but we are getting ethane. And along with that, 2NaBr, sodium bromide. Are you getting? So this is called what it is? Woods reaction. This method is not suitable for unsymmetrical alkene. Remember, this method is not suitable for unsymmetrical alkene. If an unsymmetrical alkene, then this will be different. We'll be getting the different product. Okay, example, if the two compounds we are taking, one is methyl bromide, another is ethyl bromide, then what will happen? Example, look here. If 2 moles of methyl bromide is no problem. One is CH3B or methyl bromide, sodium, Na. Okay, treat with another molecule. Like one is CH3Br, another is C2H5Br. C2H5Br. Br. We can write BrC2H5. So Br to NaBr. Then we can expect CH3 and C2H5. Then CH3, C2H5. Then what are the possibilities? It's not a symmetrical alkene. Both are not the same. If the both are not same, then possibility what will be getting? We'll be getting CH3, NaBr. Or we can get CH3, C2H5. This will be split as CH3, CH3. How it can be? This one molecule unequally can get CH3, C2H5. If it like this separated, we'll be getting CH3, C2H5. Or this will be getting CH3, CH3 in this molecule, one of the molecule, and we'll be getting. Or we'll be getting C2H5, C2H5, and getting of NaBr, sodium bromide, sodium bromide. If these may be the more, we'll be getting C2H5, C2H5 NaBr. If it is more, we'll be getting CH3, CH3 NaBr. These two combined together will be getting CH3, C2H5 propane. So for the mixture of alkane, if we take unsymmetrical alkane, we'll be getting the mixture of alkanes. So that is the reason this method, haloalkane, the preparation of alkane from haloalkane will be preferred symmetrical alkenes. Alkene what we are taking, both CH3Br, CH3Br both, or C2H5Br, C2H5Br, both the molecule, then it is symmetrical. Then will be getting the higher alkane. So third method of preparation of alkene is Woods reaction. What is Woods reaction? You have to remember. Okay, haloalkenes are treated with sodium metal in dry ether. Why we are using a dry ether? Sodium is highly reactive with water. Even it react with moisture. So free from the moisture, we'll be using dry ether. So in dry ether, we'll be getting higher alkene along with the formation of sodium halide NaX. So general formula, if you remember general formula, it is NF. Rx plus 2Na give rise to Rx plus 2Na XR. If you write like this, it will be easy. XR, this become 2NaX. RR plus 2NaX is a general formula. If you remember this general formula is kind enough for you to write the structure. Are you getting? So the third method of preparation of alkane, hydrogenation, reduction, Woods reaction. Okay, next, fourth method of preparations of haloalkane from carboxylic acid. From carboxylic acid. This also be known as decarboxylation. Decarboxylation, carboxylic acid or decarboxylation. What it is decarboxylation? Sodium salts of carboxylic acid. Sodium salts of carboxylic acid is heating with soda lime. Soda lime. Soda lime, what we are using, that is a mixture of quicklime CaO and sodium hydroxide NaOH. Soda lime is a mixture of quicklime, calcium oxide and caustic soda, sodium hydroxide. So in few of the textbook, they're given as lye, L-Y-E, lye. So lye or I-Y-E, I, what we use this is NaOH, sodium hydroxide or potassium hydroxide. Earlier the solution, both the solution is also called as I. Okay, mixture of calcium oxide, quicklime and caustic soda, sodium hydroxide is called the soda lime. Sodium salts of carboxylic acid treat with soda lime, which gives alkane. In that alkane, the containing one carbon atom less than the carboxylic acid. What we get the alkane? That is one carbon less than carboxylic acid. In this process, elimination of CO2, carbon dioxide, from COOR, carboxylic acid. From the carboxylic acid, carbon dioxide get eliminated. Hence, it is called decarboxylation. Removal of the carbon dioxide. Okay, so we'll see an example. RCOONA, RCOONA, sodium carboxylate. This is Na. RCOO minus is called carboxylate ion. Okay, this is Na, sodium carboxylate. Sodium carboxylate treat with sodium hydroxide and caustic quicklime is nothing but soda lime. Okay, and with higher temperature, moderate temperature. So what will be takes place? This will be forming n number of carbon should reduce this to n minus one number of carbon. So what we are getting, that alkane is RH. This one RH, and will be forming Na and Na to CO and O, CO3. Sodium carbonate, Na to CO3, sodium carbonate. And what we get the R value, the R number of carbon should be less than the carboxylate, what we use carboxylic group. If I take a specific example, CH3, COONA, sodium ethanoate. What is this? Sodium ethanoate, Na and CH3O, sodium ethanoate, carboxylate, and treat with sodium hydroxide, NaOH. In presence of CaO and NaOH, sodium hydroxide or calcium oxide, quicklime. Already we have written sodium now, so quicklime. When we heat this, what will happen? So this one, CH3, and for this one hydrogen will add to this. It forms CH3 and H, CH4. CH3 and H, 1 and 2 carbon. Carbon reduces to n minus 1, that is carbon number 1. Less than 1 carbon decreases from the carboxylic acid. So CH4. Along with it, an Na. This COO and O, 2 Na. Carbon 1, 2, 3 oxygen, Na2CO3, and this hydrogen binds to this, will be forming CH3CH4 plus Na2CO3, sodium carbonate. Okay, here is NaOH. Here not an Na plus and OH minus. The cleavage will take place unequally. It forms NaO, and this NaO and O and C. COONA. So COO and O is CO3. This is CO3. Na and Na2 will be getting Na2CO3, sodium carbonate. Okay, sodium carbonate. From this, what happened? Na2CO3 upon heating, it releases Na2CO3 upon heating to form CO2. Carbon dioxide get eliminated. Okay, so this is what we call as decarboxylation, removal of carbon dioxide. Hence, less than one carbon, decrease one carbon. What we get the alkene from carboxyl group. Are you getting? Are you getting decarboxylation? Decarboxylation. Fourth method of preparation is decarboxylation. Example, one more example. C2H5, COONA. C2H5 is ethane group, no? Okay, ethanoate. In that 3 carbon, ethane plus 1, 2 plus 1 is 3, that is propane, sodium propionate. This sodium propionate treat with sodium hydroxide in calcium oxide, CaO, soda lime, upon heating. So Na and O will be combined together to form Na2CO3 and C2H5 and H. It becomes C2H6 plus Na2CO3. Okay, what we are getting. So 1, 2, 3 propane N from N minus 1 is ethane, less than 1 carbon. Okay. So in this sodium salt of formic acid, so in that sodium methanoate does not give alkane or decarboxylation, because in the case of HCOONA, this is called sodium salt of formic acid. This is called sodium methanoate, only one carbon, methane OATE, methanoate. This will be treated with sodium hydroxide in presence of quicklime. Okay, so we'll be getting hydrogen H2, H and H hydrogen. Along with that, we'll be getting Na2CO3. From this, we cannot get alkane. So remember, you need to important points you need to remember. Sodium, the methanoate. This is nothing but sodium salt of formic acid, which is sodium HCOH is formic acid. No, this will be treated with sodium. Hydrogen is replaced by Na. It forms sodium methanoate, sodium salts of formic acid, which doesn't give alkene. You have to remember. Next, fifth process. Earlier, Udzria, hydrogenation. Okay, first method. Second one, reduction, zinc in hydrochloric acid. Third one, Woods reaction. Fourth one, decarboxylation or from carboxylic acid. Fifth one, next method of preparation of alkane, coal-base reaction or coal-base electrolysis. KOLBE apostrophe S, coal-base electrolytic method. So this already you know that this reaction, okay, where in electrolysis in hydrogen chapter we have written anodic cell reaction and cathodic cell reaction in same as like the same. Aqueous solution of sodium or potassium salt, aqueous dissolved, and aqueous solution of sodium or potassium salts of carboxylic acid means Na and K treat with carboxylic acid to form RCOOK or RCOONA. Sodium salts of carboxylic acid or potassium salts of carboxylic acid means which dissolves in water. On electrolysis of this, which gives even number, even number of carbon atoms, at anode. This is called coal-based electrolytic method. What is coal-based electrolytic method? And this sodium or potassium salts of carboxylic acid on electrolysis with the passing of an electric current using anode and cathode. So dissociation will be takes place at anode. Every number of atoms, carbon atom, the alkene will be forming. So example, RCOOK, potassium carboxylate. This is RCOO, this is carbon, RCOOK. Okay, potassium carboxylate. Potassium carboxylate is under electrolysis with using water. Electrolysis will be forming R. Two molecules of this will be getting R and R with the liberation of carbon dioxide CO2 with the formation of hydrogen H, liberation of hydrogen, and will be forming potassium hydroxide KOH. 2RCOOK plus H2O under electrolysis. So electrolysis, coal-based electrolytic method. Coal-based electrolytic method. So RCOOK in that. So what happened in HCOOK in that COO, carbon dioxide CO2, H and H, hydrogen gas will be liberated with the formation of R and R, 2R group. Together will be forming alkene with the formation of K and OH. This H2 mono, HOH. Okay, this will be RCOOK and RCOOK. Okay, what will happen? This is CO2 and CO2, 2 CO2. This R and R will be forming R, and this K and K combines with this 2 OH, HOH and HOH will be forming KOH. Left behind this 2 is liberated as H2. Okay, are you getting here? This potassium carboxylate treat with water will be getting R and R, 2 molecules RCOOK. RCOOK. So this one COO and COO, carbon dioxide CO2. K and K get separated. R and R, 2R plus 2 CO2. This K is K as it is, and 2 molecules of water HOH and HOH. Okay, this H and H is H2. K plus and OH minus will be forming 2 KOH. This is a product of what we are getting. Okay, this is coal-based electrolytic method. In this, we cannot able to prepare the first carbon because the carbon needs to R means need to consist of 2 carbon. From this method, we can't able to prepare methane. Okay, coal-based electrolytic process, we cannot able to prepare methane. From that, after ethane, propane, butane, we can able to prepare. But this carbon which gives at anode are even number of carbon. That's what it will be gas eliminated. But what if the gas? What the gas is liberated at anode? That should be carbon. Means the number of carbon, hydrocarbon will be liberated. So this cell reaction. Positive is anode, negative is cathode. Okay, in electrolysis process. This dissociates CH3COOK, 2 molecules, no, NFPS, under electrolysis, under electrolytic process or electrolysis, will be forming CH3COO minus, 2 molecules of CH3COO minus and 2 K plus. Right? This will be dissociation. At anode. So the negatively charged ion of 2 CH3COO minus, 2 molecules of CH3COO minus, like 2 CH3COO minus, CH3COO minus will be gaining 2 electrons. If it takes in 2 electrons, so 2K plus is nothing but this loss of the 2 electrons. So which will be forms CH3COO dot radical or CH3COO minus radical. In that the COO gets separated with CH3 and CH3. How it will be? It forms CH3 dot and CH3 dot combines together to form CH3, CH3, C2H6. And this CO and CO will be forming carbon dioxide, CO2. What it forms is ethane at anode. Ethane is liberated. It's a gas, no? Gas, hydrocarbon, which will be liberates. And at cathode, this is at anode, positive charge. Okay, this will be forming and hydrogen, that is 2H plus gains in 2 electron, will be liberated as hydrogen gas H2. At cathode, hydrogen gas will be liberated. At anode, then carbon dioxide and that's respective hydrocarbon gas will be liberated. Will be having an even number. Even number. Are you getting? So in this process, we cannot able to prepare methane because minimum the carbon number, carbon means 2 carbon is required. Are you getting? These are the important methods of preparation of hydrocarbons, alkanes. In that, so you need to be studying the next year is an important one more reaction. So additionally, you have to know that, okay, in the 2 reaction out of that, methane, CH4, can be prepared by the treating of the carbide like Al4C3 aluminum carbide or Be2C beryllium carbide with water. So with water. So methane can be prepared with beryllium carbide or aluminum carbide treating with water. This and also another method preparation of methane from carbide is called methanide. Methanide, or this process is known as methanide. NID, MEDHA, NID, methanide. So example, Al4C3 aluminum carbide treat with water H2O will be getting AlOH thrice plus CH4 methane. Okay, so this one Al4C3 aluminum carbide treat with water will be getting the methane, method of preparation of methane. Additionally, you have to remember. Next, one more important the process in next year, it's 2 important process what we are studying is from preparation of alkene from Grignard reagent. Grignard reagent. Grignard reagent having a general formula RMgX, alkyl magnesium halide. Alkyl magnesium halide. This is the general formula of Grignard reagent. So you need to remember, it's too important for the further in next year. It's too important. What is Grignard reagent? Or MgX, alkyl magnesium halide. Are you getting? So this Grignard reagent is treated with so the compound like water, protonated compound, or the protonic compound like which one donates protons like water in H2O in carboxylic acids or alcohols or amines. So what happens to this R and MgX? This part, MgX part of the reagent is replaced by hydrogen to form alkane. To form alkane. Remember, when Grignard reagent is treated with protonic acids like carboxylic acids or alcohol or amines or etc., then MgX part is replaced with hydrogen RH and Mg. First additional compound, adduct compound will become formed, then it will be dissociated. Example, CH3MgI, methyl magnesium iodide, treated with C2H5OH, ethanol. So what happened? This one CH3 and this is MgX part which attaches to the hydrogen, that is CH3H is nothing but CH4, CH3H. Remaining is C2H5O combined with an Mg will be forming C2H5OMgI. Okay, methyl C2H5, ethyl oxymagnesium iodide. Ethyl oxymagnesium iodide. This is the adduct compound, additional compound will be forming Okay, Grignard reagent, this will be called as organometallic compound. Grignard reagent, also very familiarly we call as organometallic compound, because alkyl group, magnesium metal group, and halide group. Hence it is called organo. First organometallic compound is methyl magnesium bromide. First compound, CH3MgBr is the first compound what we get. Okay, and this will be used now in presence of dry ether, because we'll be using sodium or magnesium will be using. So to avoid the moisture content, we'll be using dry ether in this reaction. So we can able to prepare alkane from Grignard reagent. This Grignard reagent treated with the protanoic acids, protanoic compound like acids or alcohols or amines or etc. will be getting alkane. Will be getting alkene. So what is Grignard reagent? RMgX. Organometallic compound is called Grignard reagent, and its general formula is RMgX. Okay, are you getting? These are the methods of preparations of alkanes. Which are the methods? ಯಾವ methods in Avadira? What is the first one? What is the first method? No? Are you sleeping? Unsaturated hydrocarbons. Okay, first one. Next, second one. This unsaturated hydrocarbon is also known as hydrogenation. Okay, what is the second one? Good, very good. That is reduction. Reduction, that is hydrochloric acid. Hydrochloric acid, zinc and hydrochloric acid are HCl. What is the third one? Important reaction. Third one. Huh? Good. Woods reaction. Next. Fourth one. Woods reaction. Good. Next. Fourth one. Fifth. Fourth one. No. Fourth one. Before that. Before coal base. Very good. Decarboxylation. Decarboxylation reaction. After decarboxylation reaction, fifth one is coal-base. No, don't say coal-base reaction. Coal-base reaction, next we'll be studying with a different preparation of salicylic acid. That is different. Coal-base electrolytic. Good. Coal-base electrolytic method. Coal-base electrolytic method. So these are the important methods of preparation of alkene. Even along with that, next and additionally we studied from carbides, preparation of alkenes from carbides, as well as from Grignard reagents. Alkyl methyl magnesium bromide. Alkyl magnesium bromide is the first compound of organometallic compound. Inorganometallic compound, organic compound, or metallic compound Mg, and iodide means halide. RMgX is a general formula. Everyone should remember. Okay, these are the methods of preparations of alkene. Okay, how to remember? You need to practice that. That's not difficult. Just you need to practice. Okay, next. Physical properties. Physical properties. In these physical properties, first one, how it will be exist? C1 to C4, carbon 1 to carbon 4. These alkanes means methane, ethane, propene, butene. These are colorless, odorless gases. Colorless, odorless gases. No color, no smell. And C1 to C4 are the gases. Okay, and C5 to C17 are colorless liquids. C5 to C17 are colorless liquids. C18 onwards, carbon 18 onwards, these are the waxy white solids. Waxy white solids. Carbon number 1 to carbon number 4 are colorless, odorless gases. I said in ethane, methane, propane, butane, at anode, the alkenes are liberated. These nothing but they are gases. Okay, C1 to C4 are colorless, odorless gases. C5 to C17 are colorless liquids. 10 to 17, you need to remember. 18th onwards, waxy white solids. Waxy white solids. Vaseline. We are using cold moisture creams. White solids, jelly, waxy, like jelly. Okay. How it will be exist? This is in a physical state. Second one, the boiling points. Boiling points of the alkenes are lowest of all the group of organic compounds. In all the group of organic compounds, these are the lowest. This is because the molecular interaction is weak. Weak force of attraction between them is weak force of attraction. Hence, the boiling point of alkene increases with increase in more number of carbon. Okay, more number of carbon is nothing but increase in carbon chain or molar mass. Molar mass. If the molar mass increases, no, so surface area increases. If molar mass increases, surface area increases. If surface area increases, then the boiling point increases. Boiling point of alkenes is lowest of all the organic compounds. Okay, because weakest intermolecular force of attraction, weak force of attraction between them. The boiling point of alkene increases with increase in molecular mass. Molecular mass increases because of the surface area increases, then the boiling point increases. Next, we know that isomeric compound. In isomeric compounds, with increase in branching, so boiling point decreases with increase in branching. Okay, branching increases, more number of branching. There will be steric endurance, repulsive force between them. The force of attraction decreases, the boiling point decreases. Boiling point decreases with increase in branching. And last class, I said, I hope you remember the pentane, butane and pentane. We said in normal pentane that is 309 degree, in neo 309 Kelvin. In neopentane, that is 283 Kelvin, the large difference. In between, that isopentane is 301 Kelvin, is nothing but, so normal pentane to isopentane, 109 to 309 to 301 Kelvin, temperature, boiling point decreases. From isopentane to neopentane, further it will be decreases from 283. 283 is nothing but so normal pentane, that is greater boiling point is greater than isopentane is greater than neopentane. Boiling point decreases with increase in branching. More branching in the boiling point is less. Endurance is more. Okay, steric endurance is more. Okay, next. Solubility. So these are insoluble in water because being a non-polar molecule. These are a non-polar molecule. Non-polar molecule obviously insoluble in water. Insoluble in water. But the soluble in non-polar solvents like benzene, toluene, C6H5CH3, alcohols, ethers, or etc. In this will be soluble. These are the important physical properties you need to remember. Priyanka, in alkenes there will be sigma bond, should be having a high boiling. Sigma bond will be having in a sigma bond only, means sharing of the pair of electron between them. So this means carbon hydrogen electronegativity difference is less between them is less, and in compared to carbon-carbon straight chain, what we are getting carbon-hydrogen bonding, in that out of all the organic compound, this will be weakest, is nothing but there will be weak force of attraction between them. Okay, the sharing of electron between them. Okay, not complete transfer. If it is transfer, no, obviously should have a high melting point and boiling point. Okay, in ionic compounds, we'll be having a high melting point and boiling point, complete unequal distribution of masses. Here, it's not like this. Okay, it's not like that. Are you getting? Okay. These are the physical properties. Physical properties. In the physical properties, what do you need to? So C1 to C4 are colorless, odorless gas. C5 to C17 are colorless liquid. C18 onwards, waxy white solids. Then see, in the case of second one, boiling point. So boiling point will be the lowest in all the group of organic compound because we'll be having biggest intermolecular force of attraction. Okay, weakest force of attraction, and with the increase in the molar mass of the carbon, means molar mass increases, surface area increases, then the boiling point increases. Boiling point decreases with increase in branching. If the more of branching, the more of repulsive force between them, then the boiling point decreases. Next, solubility. It's being a non-polar. Being a non-polar, it is insoluble in water, soluble in organic solvents like benzene, naphthalene, toluene, alcohol, ethers, or etc. These are the compounds. Are you getting? So what we are studying till now, what we studied in earlier from hydrocarbon. So saturated, unsaturated, double or triple bonded, and aromatic. So the types of the hydrocarbon we studied. And after that, we studied about the complete, means in detail, structure of alkenes. Studied structure of alkene. Next, after that, then isomerism. Isomerism led to chain isomers. We didn't study conformations. We need to study conformations later. Then after that is, sorry, here in the nomenclature. So after this is nomenclature. Already we studied, just very recall. And after that, isomerism. Next, after that, that's alkene. In that alkene, preparation, method of preparation of alkene. Next, after that is physical properties of alkene. Are you getting how it is following? In which order you are studying physical properties? After physical property, next is chemical reactions. Chemical reaction. After chemical reactions, conformation, carbon-carbon rotation, free rotation, which leads to the conformation. Similarly, we need to study about other compounds also. Okay. We'll see chemical reactions. Chemical reactions. In chemical reactions, in the first place, alkenes are inert at normal condition. Inert. That's the reason we got a name of paraffin. Paraffin, the Latin word, is nothing but less reactive. Affinity, little reactive. So less affinity. So that is a word what we get. The alkenes are inert in normal condition. That is the reason that doesn't react with acids, bases, or any other reagents. So that is the reason we use a word of paraffins. Little affinity. Okay, we'll be having little affinity. But this alkane undergo substitution reaction under normal condition. So addition of an acid, reaction with the acid, bases and other hydrocarbons or other group or other reagent is neglected, and we can show it can show substitution reactions. Okay, 1 minute. Alkanes will show substitution reaction. These are inert towards a chemical reaction. So it doesn't react with acid bases or any other reagents. Okay. In substitution reaction, what is substitution reaction? We studied in earlier chapter. Any one of the group is replaced. Hydrogens, one or more hydrogens are replaced in alkane. Okay, replace, substitute in alkane is called the substitution reaction. So this substitution may be the halogen. Halogen may be substituted, or halo group can be substituted. Sulfonation or sulfonic group. Halogen X group, SO3H is sulfonic group. Sulfonic group can be replaced, or any lower alkenes. If you consider any group can replace that. In any lower alkane, do not undergo nitration. Lower alkenes means smaller alkene, carbon number lesser, that doesn't undergo nitration and sulfonation. But halogenation reaction takes place when at any temperature, usually at higher temperature. In the case of chlorine and bromine, iodine is higher side, and chlorine, bromine, the required high temperature. So approximately how the chlorination reaction will be takes place, and approximately 573 to 773 Kelvin. The chlorination reaction is nothing but photosynthesis reaction, no? So diffusion of sunlight. So chlorination reaction will be takes place in presence of sunlight or UV, ultraviolet light. The chlorination reaction is if in all hydrocarbon, irrespective of the number of carbon. So chlorination reactions or halogenation reactions will be take place. We'll see halogenation substitution reaction in that halogenation reaction. Halogenation reaction, first one, methane. So carbon with the 4 of hydrogen, carbon, hydrogen, 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 4 hydrogen. Treat with chlorine in presence of sunlight, HCl. So what will be getting? CH3Cl, methyl chloride, with the formation of hydrogen, right? Next, what we get the methyl chloride, CH3Cl, treat with again chlorine, Cl2, in presence of HCl, sunlight. We'll be getting CH2Cl2. Okay, 4 of hydrogen, now 1 hydrogen is replaced with chlorine. Then CH2Cl2 plus HCl. Okay, then 2 hydrogens are replaced by chlorine. Next, CH2Cl2, dichloromethane, treat with chlorine in presence of sunlight. We'll be getting CHCl3, trichloromethane with the HCl. Trichloromethane. This trichloromethane, CHCl3, treat with chlorine in presence of sunlight. We'll be getting carbon tetrachloride with the formation of hydrochloric acid. This is a chlorination reaction. In carbon, we'll be having an hydrogen when we treat with chlorine Cl2. So keep on replaces 1 with chlorine, it forms an CH3Cl. Second hydrogen with another chlorine, then CH2Cl2. Third hydrogen with another chlorine, CHCl3. Okay, trichloromethane, and again treat with CH3Cl with chlorine, will be getting CCl4, carbon tetrachloride, along with the formation of hydrochloric acid. Okay, so this is free radical mechanism, which is free radical mechanism of methane. So what is free radical mechanism? How it will be takes place? So this mechanism carries three important steps. First step, what begins? Reaction will be begins. That is called initiation. INITION. Initiation. So initiation begins. If it begins, then it will be continuous. No, then it is movement. We call it as propagation. Initiation, then propagation. It keep on moving. After propagation, at last it should end. Third one, termination. Termination. 3 steps. Initiation, propagation, termination. Begins, no, that is in the form of chain. Chain initiation, chain propagation, chain termination. Begins the reaction, initiate. Propagates, keep on continuing. Terminate, ends. Okay, so free radical mechanism will be consisting the 3 steps. So reaction, how methane methyl group, okay, that is NCH4 and 3 HCH3 methane, treat with chlorine CH2. Will be getting, means in presence of sunlight, means approximately 522 670 Kelvin, will be getting CH3Cl methyl chloride and HCl. So how this will be begins? When the reactants are consumed completely, then the reaction terminates. Till to reaction continues, so propagation. Reaction needs to begin initiation. In chain initiation, what will happen? Chlorine in the first step, Cl2 will be Cl and Cl. So will be takes place in homolytic fission, half hook, half fish hook. Fish hook or half arrow. We call it as a fish hook or half arrow. That what happened? Homolytic fission equally will be dissociates to form Cl dot and Cl dot forms an free radical. Cl dot and Cl dot free radical. This is the chain initiation. When chain initiates, starts, then it will be continuous propagation. Chain propagation, one of the chloride free radical of chlorine attached to the methane group CH3 and H, which is replaced by this free radical, means this free radical replace this hydrogen, substitution, or this can be combined. This can combines with this, okay, substitute this hydrogen or combine, it can easily combine Cl dot and H. So what happens? H will be removed from this. If HCl are removed, then we'll be having only one electron. This is free radical. It will take one electron. Then one electron will be left behind on CH3. Please kindly understand. Left one CH3, one radical will be left behind on CH3. So one electron will be taken from the chlorine with a hydrogen, will be forming HCl, right? So it forms an CH3 radical. This CH3 radical, CH3 dot, combines with again Cl and Cl. Again, what will happen? Fish hook, half homolysis. Cl dot. Cl dot what happened? Again CH3 and Cl. One will be combined with chlorine, CH3Cl. Another will be forms a free radical. One is CH3 with Cl. It forms CH3Cl. If it removes one chlorine, Cl will be having free radical. This Cl again replaces one of the hydrogen, free radical. So it will be continuous till to replacing of all hydrogen. At last, third one, termination. In termination, Cl free radical of Cl dot and Cl dot. This will be combined together to form Cl2. All this will be CH3 radical, CH3 dot and the CH3 dot free radical combined together will be forming CH3, CH3, C2H6. This is the chain termination. So reaction is this mechanism. Reaction how? CH4 replaces all the hydrogens are replaces with chlorine will be forming carbon tetrachloride. How it is the chlorination of methane? How the process will be takes place? Chain initiation, chain propagation, chain termination. Look here, I'm saying this is a reaction. If in the reaction, CH3H, methane state with a chlorine, will be getting CH3Cl and HCl. How we are getting this? How we are getting this? Chain will be initiates. Cl2, chlorine homolytically separates, homolysis will be forming Cl dot and Cl dot, free radical will form. So this will begins the reaction, chain initiation. When it begins, CH3H in methane, free radical, one of the free radical, one is left behind, one of the free radical combined with this hydrogen will be forming HCl. What is the left behind thing? CH3 dot and Cl dot, right? So this Cl dot and CH3 combined together to form CH3Cl, and again one chlorine will be left behind. So it will be continue till to replacing of all the chlorine with hydrogen. At final means how it will be end. Cl dot and Cl dot combines together to chlorine, and CH3 dot CH3 dot combines together to form C2H6. This is how the reaction will be ended. So you need to remember chlorination of methane important. Chain initiation, chain propagation, chain termination. Are you getting how this reaction? Everyone should able to write this important question. Okay, so halogenation reaction. In that halogenation, that is free radical mechanism, especially for chloromethane. CH3Cl, how it will be forms chlorination, chloromethane, halogenation or free radical mechanism of chloromethane. How it will be takes place. Methane CH4 or treat with chlorine, will be getting CH3Cl and HCl. How this mechanism will be takes place? First, this with the formation of this chain initiation, chlorine equally dissociates. Homolytic cleavage will takes place to form Cl dot and Cl dot. Then CH3, one of the chlorides, chlorine free radical combined with hydrogen to form HCl and will be forming the methyl radical, methyl free radical CH3 dot. If CH3 dot combines with the CH3 dot, reaction ends. That is termination. Are you getting? Cl combines with the Cl dot to form Cl2. Chain initiation, chain propagation, chain termination. Are you understanding? Are you getting this? Okay, is an important free radical mechanism of methane consists 3 steps: chain initiation, chain propagation, chain termination. Initiation begins, propagation carrying the reaction, carried out reaction led to the replacement of all hydrogen with chlorine. Termination, finally it will end. How it will be ends. Are you getting? Okay, so this is important. Yes. Yeah. 3 steps. You need to write how this. If you write chain initiation, chain termination, and chain propagation and chain termination, with this is enough for us. Yeah. Okay. In this reactivity of hydrogen atoms in this free radical mechanism in chlorination of methane. In this, how we consider the hydrogen atom, reactivity of hydrogen atom. Usually tertiary hydrogen is more reactive than primary. And the order of halogens also, fluorine is extremely more reactive. F2 is extremely more reactive than chlorine, than bromine, than iodine. Okay, so compared to the halogens in the order. Fluorine is violent reaction, so it's very difficult to carry out or difficult to control. Hence, that is reaction. Fluorine reaction is also known as dark reaction, carried out in absence of light, because in normal sunlight itself it will react. We studied about fluorine, how so reactive it is. Instead of fluorine, we'll be using chlorine, bromine, or iodine. Okay, iodine is very slow reaction and it's reversible also. Therefore, it will be carried out in presence of oxidizing agent. Iodine will be carried out in presence of oxidizing agent like HNO3 or hydroiodic acid HiO3 or etc. In the presence of oxidizing agent, it's a slow reaction. Iodination itself is a slow reaction and reversible. Hence, in presence of oxidizing agent, which will be carried. Chlorine and bromine reaction will be takes place at moderate 520 Kelvin itself. The reaction will be takes place. Okay. So, in the chemical reaction, in the chemical properties, the first one, free radical mechanism. Next, very famous reaction, what we practiced is combustion, burning, combustion. Okay, combustion of alkenes, combustion of methane is what we study. In that combustion, there will be a two different, whether the hydrocarbon completely combines with oxygen or partially combines with oxygen. We call as complete combustion. Combustion of or oxidation, what we consider now, complete oxidation is combustion, or incomplete oxidation too. In that we need to study. In few of the cases, we can able to control this. Okay, incomplete means insufficient. Means we can moderately control. If it controls, then it is called controlled reaction. So first one is complete combustion. Complete combustion. Second one is incomplete combustion. Incomplete combustion. Okay. Oh no, I'm not writing in English, no. Okay. Incomplete combustion, complete combustion, and incomplete combustion. And we can able to control the oxygen with the controlling the suitable condition, that is called controlled oxidation. 3 types. Okay, in that major 2 types, with the using of suitable conditions, this is controlled oxidation. Combustion, you know that with the using hydrocarbon and combustions to form carbon dioxide and water. Familiar reaction, I think doesn't require to explain much. So large amount of heat will be liberated. So general formula, I'll write general formula, need to remember. CnH2n plus 2 alkane, which on combustion O2 will be gives carbon dioxide NCO2 plus H2. So here 3n plus 1 by 2, 3n plus 1 by 2 and NCO2 and n plus 1 H2O plus heat. This is a general equation. Cn H2n plus 2. 3n plus 1 by 2 O2. This much of oxygen will be consumed to form NCO2, n number of carbon dioxide, n carbon number of carbon number of carbon dioxide. So sorry, n number of carbon dioxide and n plus 2 number of water molecule. Okay, example, methane, CH4. CH4 on combustion, O2, give rise to, we know that CO2 and H2. CO2, CH4, on combustion, will be getting 3n plus 1, C1, 3 plus 1, that is equal to 4. 4 by 2 is equal to 2. CH4 plus 2 O2, give rise to. So, in presence of, we'll be using anything, we can bonds, means in oxygen, air or provided atmosphere, oxygen atmosphere, will be forming carbon dioxide. Carbon dioxide N is 1 CO2, the same as CO2, plus N plus 1, that is 2H2O, plus heat. How much? That is, how much value? Where it is? 212.8 kilocalories per mole. This is heat liberated generally. Okay, so 3n plus 1 of O2 and n plus 1 CO2 plus n plus 1 number of water molecule will be formed. So remember this general equation. CnH2n plus 2, 3n plus 1 by 2 O2 give rise to NCO2, n plus 1 H2O. This is complete combustion. Incomplete combustion. First one, this is complete combustion. Second one, incomplete combustion. In the case of incomplete combustion, this insufficient amount of oxygen is provided to that, to burn an hydrocarbon. To that, carbon black is more. It forms a more of carbon. So it is used. This is also used. One of the use also. This is used in the preparation of ink. This incomplete combustion used in the preparation of ink, and the black pigments or the filters. Okay, we'll be using the filters or black pigments we can able to prepare from incomplete combustion. So if the same of methane on the incomplete combustion, so insufficient of air or oxygen to, so CH4 plus O2 give rise to CO2 and H2O is insufficient, will be forming carbon monoxide. Will be forming carbon monoxide. C3n plus 1. No? So CH4 plus 3O2 give rise to 2CO plus H2O. H2O 2, 4. So 4H2O. And with the liberation of heat, this is incomplete combustion. In incomplete combustion, the carbon black is more. If carbon black is more, that is what we are using. Methane, CH4, treat with oxygen, will be forming carbon black with a formation of H2O, water. Okay, this is carbon black. Carbon black used in the preparation of ink, black pigments. Black pigments. This is carbon black. Okay, this is incomplete combustion. Due to incomplete combustion, only the pollution is more. Okay, next, third one is controlled oxidation. Controlled oxidation. In the case of controlled combustion or controlled oxidation, these alkanes are heated with minimum, means regulated. We can control this oxygen, regulated supply of air or oxygen O2 at high pressure in presence of using suitable catalyst. Using catalyst, what it gives the product are called. Yeah, tell me, what's this? Yeah. What it gives the product or the respective, means the respective group, substituent group will be added to that. We can able to prepare alcohol or aldehyde. We can able to prepare from controlled oxidation. So example, methane, CH4 on oxidation O2, controlled oxidation. In controlled oxidation, we'll be using catalyst copper at 523 Kelvin and 100 atmospheric pressure. So the CH4, two molecules of CH4 can be combined together. CH4 and CH4, this oxygen O and OH will be combined together. Two of oxygen in that will be combined together to form CH3OH, that is an alcohol. So what it gives, the different oxidation compound, means oxygen will add to this, will be forming alcohol. Similarly, the methane on combustion, 1 mole of methane on combustion, CH4 on controlled oxidation in presence of the molybdenum oxide, MO2O3 molybdenum oxide, MO2O3 molybdenum oxide will be forming HCHO formaldehyde with a formation of water molecule. Means different oxidized compound will be getting C2H6 ethene on treating in presence of the manganese acetate will be getting the carboxylic acid HCOOH. So based on what we are using, the compound, means based on the suitable condition, means with the regulating air oxygen will be getting different oxidized compound, means oxygen will be added to hydrocarbon. It can able to form aldehyde or alcohol or carboxylic acids. Okay. Ordinary alkanes resist oxidation. Okay. Ordinary alkanes ordinary alkene resist oxidation, but alkenes having tertiary or 3-degree hydrogen atom can oxidize to corresponding alcohols by KMNO4, potassium permanganate, KMNO4, with the using of potassium permanganate. Okay, ordinary means straight chain alkenes. In alkenes, what we consider are the normal ordinary alkenes resist oxidation. But alkenes having tertiary 3-degree hydrogen can oxidize to the respective alcohol, can oxidize to give an alcohol in presence of potassium permanganate. Example, CH3 thrice 3 CH3 molecule and carbon will be having CH. So this will be called as 2-methyl propane. This will be treated with oxygen in presence of potassium permanganate, KMNO4. So 3-degree hydrogen now. So what will happen? The replacement means oxidation will be easy. CH3 thrice and carbon hydrogen oxygen will add to this, will be forming CHO, CH3, CHO. It forms propanol, 2-methyl propane to all. Forms propanol, 2-methyl propane to all. So normally our ordinary hydrogen resist oxidation, and the hydrocarbons or alkenes having tertiary 3-degree hydrogen can easily combine with oxidation reaction in presence of potassium permanganate is an alcohol. Okay, these are the oxidation of reaction: complete combustion, incomplete combustion, controlled oxidation. Complete combustion, standard equation. Incomplete combustion, what impurities, so not what impurities, what carbon means. Incomplete combustion leads to formation of what we call as a pollution. Is the same as a pollution rich of carbon content. Okay. Third one is controlled oxidation with a regulating oxygen. We can able to prepare the oxidized compound like alcohol, aldehyde, ketones, or carboxylic acids. Okay. This is another chemical reaction. And we know that isomers, how the chain are separating. Okay, so chain are separating isomerization, or that is a process. In that, normal or straight chain alkanes on heating in presence of anhydrous aluminum chloride, AlCl3, and hydrogen chloride, HCl. So that straight chain is turned into a branched chain. Example, CH3, CH2, CH2, CH3. That is 1, 2, 3, 4 butene. butane and treat with aluminum chloride in presence of anhydrous aluminum chloride and HCl at 300 degrees Celsius. This will be getting a branched carbon, branched butane like CH, CH3, CH3, and CH3. So this is isomerism, means straight chain hydrocarbonyl alkane are heating in presence of anhydrous aluminum chloride and hydrogen chloride, HCl gas. So branched isomers will be forming. So similarly, an hexene treat with anhydrous aluminum or pentane treat with anhydrous aluminum chloride will forming normal pentane to isopentane and neopentane. Okay, so and this is another chemical reaction, isomerization. Alkenes are treated with anhydrous aluminum chloride. Anhydrous, apart from moisture content in aluminum chloride, these gases are responsible for the breaking of hydrogen compounds. Okay, we'll be getting the break into attached to some other group, then more repulsive. Even it is unstable, the compound will be exist compared to normal and branched chain. Branched chain is always unstable than normal chain because of steric hindrance. Okay. Next, from using straight chain, we can able to prepare the closed chain. Is called aromatization. Aromatization, aromatic is benzenoid compound. Aromatic means aromatization. That is called aromatization. I'll close within 5 minutes. Need not to get ready. Okay. Aromatization is nothing but normal straight chain alkane are treated with chromium oxide Cr2O3 or aluminum oxide A2O3. Chromium oxide or aluminum oxide with the using of the platinum catalyst PT. At 600 degrees Celsius, we can able to prepare cyclic compound like aromatic compound benzene. Aromatic compound benzene. 6-membered carbon. 1, 2, 3, 4, 5, 6. Okay, 3 plus 3, 4, 6. This 6-member carbon can be written like 1, 2, 3, 4, 5, and 6. Okay, but first carbon and last carbon doesn't link here. CH3, rest will be CH2 and this CH3. The rest of carbon will be in CH2. This is called as normal hexane, N-hexane. This will be treated with chromium oxide, Al2O3 aluminum oxide, or platinum catalyst at 600 degrees Celsius. So what happens in here? Dehydrogenation, removal of hydrogen will be takes place and the bond will form H2. One hydrogen and one hydrogen will be removed from this. If the two are hydrogen removed, it becomes CH2 and CH2. Then will be forming benzene with the liberation of dihydrogen. 2 plus 2, 2 molecules. So 2 are 2, the 4 H2. Because and the two hydrogens will be combining now CH2 and CH2. 2 hydrogen will be liberated with the formation of aromatic compound of benzene. So aromatization. What is an aromatization? With usually 600 to 773 Kelvin temperature and 10 to 20 atmospheric pressure. We can get cyclic compound or cyclized compound. What we are getting are the petroleum products in refining, in purification or in aromatization process is petroleum reforming process. This is also known as petroleum reforming process. This is also known as petroleum reforming process. Aromatization means normal straight chain compound are treated with chromium oxide or aluminum oxide in presence of the platinum catalyst at 600 to 773 Kelvin temperature will be getting benzene. Similarly, heptane are treated will be getting methyl benzene CH3, C6H6CH3 and with the liberation of hydrogen. Okay, and only one more reaction and we'll continue in the next class. So this is, I said in the beginning, small chain hydrocarbons are more stable. We call as so this long chain hydrocarbon break into a smaller chain hydrocarbon because in that it will give more efficient energy. Efficient energy or more energy. That is called pyrolysis. Pyrolysis or thermal cracking. Pyrolysis or thermal cracking. Name itself indicates pyrolysis, heat. With the supplying of heat, compound gets separated. Thermal cracking, with the supplying of heat, we can crack the compound. From this, the process of breaking down of higher alkane into a lower alkane. Process of breaking down of higher alkane into lower alkane. At higher temperature, this is known as thermal cracking or pyrolysis. Okay, in this, what happened? Example, C12H26 is called dodecane. Dodecane. Higher C12 carbon. This will be treated with platinum or palladium catalyst or nickel catalyst at 973 Kelvin, higher temperature. This C12 compound splits into C7H6F3 and C5H10 compound, another product. So 12 compound splits will be forming smaller compound. Okay, decane, when we heat that, it will be forms C10H22 decane, the same platinum, palladium or nickel at 973 Kelvin, which will be getting C2H4, that is ethene, with the formation of C8H18. C8H18. Here C5H10 is pentene, and on alkene, here also heptene and heptene here. So C8, this 12 dodecane splits into, will be getting heptane and pentene, and here C10 decane at higher temperature break this into form C2H4. Okay, C2H4 is ethene, other product with the formation of C8H18. C8H18 is octane, and this is ethene, the compound. This is called pyrolysis or thermal cracking. Methane on the pyrolysis will be getting carbon black. So this will be used as carbon black paint. How we are getting a black paint? Methane, CH4 on thermolysis. Thermal means 1000 degree. So methane on pyrolysis or higher temperature, when we heat higher temperature, will be getting carbon and 2 hydrogen. This carbon only we call as the carbon black will be using in printing machine. What we are using in earlier carbon sheets, we are using black carbon. Nowadays we are not using. Earlier we used to write blue and black carbons. That carbon sheets are prepared from this black carbon and ink. Okay, black, which is used for the printing. What we are using is the carbon black. Okay, this is pyrolysis or thermal cracking. As like this methane heat at higher temperature means normal, means steam. When the reaction with the steam, methane reacts with water, H2O. So in presence of nickel catalyst at higher temperature, 2270 Kelvin, will be forming carbon monoxide and liberation of trihydrogen. So the C is what the reaction with the steam. Methane reacts with steam, it forms carbon monoxide and dihydrogen. These are the chemical reactions. Last part is the confirmation. I'll continue in the next class. So here, what are the chemical reactions we studied from the beginning? Reverse order. We studied heat reaction with the steam, methane. Means alkane. Next, pyrolysis, thermal cracking or pyrolysis. Earlier we studied aromatization, right? Aromatization, cyclic ring. Before that we studied oxidation. In that oxidation, complete oxidation, incomplete oxidation, controlled oxidation, right? And before that we studied free radical mechanism. So in free radical mechanism, especially mechanism of methane, free radical mechanism of methane we studied. That is, these are the substitution reaction, alkenes and substitution reaction, because it doesn't react with acid, bases or other compounds. Okay, so conformation will study in the next class. Conformation will be continue in the next class. Are you getting? Are you understanding? Are you